6.3 Part 1 video. Our objective for this lesson is going to be to identify and evaluate exponential functions. Okay. So first we need to talk about what an exponential function is. First and foremost, it's a function, which means that every input has only one output. Meaning if I put in a 6, like down here, if I put in a 0, the only possible output is a 2. Okay, I can't put in a 0 later on. I can't put in a 0 later on and get out a 12. Okay, that wouldn't work. It wouldn't be a function. Okay, but this is a special type of function. It is an exponential function. What we mean by exponential function, first and foremost, means it's nonlinear. It does not graph a line. Does not graph a line, so it's not going to graph a straight line. Does not graph a line, so that it doesn't have that constant rate of change like a linear function does. Our most standard linear function, was y equals mx plus b. That was our linear function. Okay, where it had a slope and a y-intercept. Exponential functions do not have a slope. They do have a y-intercept, and we'll talk about that in the next part when we get to graphing. But they do not have a slope because they're not linear. Exponential functions are primarily its parent function are of the form y equals a times b to the x. I want you to notice where the variable is in this case. The variable is in the exponent, hence it being called an exponential function. So in this function, I'm multiplying b times itself so many times, x times, then multiplying it by a. Okay, so I think the easiest way to talk about an exponential function is to go ahead and look at an example of one. So let's go ahead and look at the function y equals 2 times 3 to the x. And a lot of times it's written this way, sometimes with parentheses. 2 times 3 to the x, we just omit the dot and do parentheses instead. These mean the same thing. So if I wanted to create a table of values for this, okay, I can create an XY table over here. So go ahead and create an XY table in your notes. And I can put numbers in. Like I can start out by putting in a 0. Okay, when I put in a 0, this would give me 2 times 3 to the 0. Well, we know anything to the 0 power is 1. So I would take 1 times 2, which is 2. So an input of 0 gives me an output of 2. If I put in a 1, 2 times 3 to the 1, I have to do exponents first. So I do the 3 to the 1 first. 3 to the first is 3 times 2. This gives me an output of 6. Okay, put in a 2. 2 times 3 to the second. Again, exponent first. 3 to the second. 3 times 3 is 9. Times 2 is 18. Okay, we put in a 3. 2 times 3 to the third. 3 to the third is 3 times 3 times 3, which is 27, times 2, which is 54, and so forth and so on. Okay. But what we notice is, unlike a linear function, if we look at the pattern here, my x's are going up by 1 each time. That's just the numbers I picked, just so we can look at this pattern. But look at my y's. This one goes up by 4. This one goes up by what, 12? This goes up by a whole lot more. Since it is not linear, it does not have a constant rate of change. Okay, so over here does not have a constant rate of change. But what it does have is, instead of looking at this going up by 4, 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. It goes up by what we call a factor, because I multiply by 3 each time. Multiply by 3. And actually, let's fix that notation. Instead of a multiply sign, let's put dot. Times 3, times 3, and then 18 to 54 times 3. So instead of a constant rate of change, it's multiplied by a constant factor. It has a constant factor. So the outputs go up by a constant factor. So that's really how we tell whether something is linear or exponential. Okay, so here for this example 1, on this first one, first we want to look to make sure x's go up by the same amount. 0 to 1, 1 to 2, 2 to 3. Yep. So these all go up by 1 each time. Up by 1, up by 1. And then now we look from here. Do they go up by the same amount or do they go up by the same factor? 2, 4, 6, 8. Looks like it goes up by 2. So since we add 2 each time, that tells me that it is a linear because of that constant rate of change. It's going up by 2 each time. Okay. Well, on this next one, if we notice our x's here go up by 1 each time, 0 and 1, 1 plus 1 is 2, 2 plus 1 is 3, up by 1 each time. But look at from here, add 4 to get to 8. I don't add 4 to get to 16. 4 times 2, dot times 2, is 8. 8 times 2 is 16. 16 times 2 is 32. So that makes this one exponential because of that constant factor. Factor is a multiplication word. Factor is the numbers. A factor is the numbers that you multiply, is what a factor is. So if I took 3 times 6, 3 and 6 are factors. Those are both factors. And what they equal over here is what we call the product. Sorry, I had to get kind of tiny, squished over there, is the product. So 18 would be the product. So since it has a constant factor of 2, it multiplies by 2 each time. That tells me it's exponential. Okay. Now, last part for this video, example 2, we're going to evaluate each function for the given value of x. So this tells me that here is my function, negative 2 times 5 to the x, and I want to put in an x equals 3. So the first thing I'm going to do is replace my x here with a 3. So y equals negative 2 times 5 to the third. That's a times. Order of operations, you have to do exponents before you multiply. So I'm going to have to take the 5 to the third first. So take 5 off to the side. I'm going to take 5 times 5 times 5. Or grab my calculator. 5 times 5 is 25. Times 5 is 125. So I have negative 2 times 125, which gives me a negative 250. So this is saying when I have an input of 3, again, this is my input of 3, my output is negative 250. Okay. Let's go ahead and let's look at another one. Okay, so here is my function. Y equals 3 times 0.5 to the x, and I want to put an x equals negative 2 in it. So again, I'm replacing this x here with a negative 2. Again, notice how I show my work. I write the problem down, I plug my number in. It's a good thing we did negative exponents already because I know what that negative 2 is going to do. It's going to take the reciprocal. Again, I have to do my exponents first, so that would be 1 over 0.5 to the second times 3. So at this point, we could use our calculator. 1 divided by 0.5 to the second is 4. Look at that, it's 4, because guess what? 0.5 to the second is 1/4. If we did it without a calculator, 0.5 is the same as 1/2 is what I would do. 1/2 times 1/2 is 1/4. And then I would need the negative. This is just 1/2 to the second. And then to get the negative exponent, you take the reciprocal. So this would be 3 times, instead of 1/4, 3 times 4, which is 12. So an input of, again, an input of negative 2 gets me an output of 12. Now I want you to go ahead and do these problems on page 310, 6 through 20 even.